Sinistra.
Sinistra, that's it.
I would really love to see you start calling someone Hamilton.
Never done my child. They used to like tie people's left hands behind their back.
Yeah.
Have you ever considered, like, what if you got it wrong? Like, what if I'm actually right-handed, but on the first day I started writing, I decided that I picked the wrong hand, and I just got used to it.
I mean,
that's
like,
makes
handedness
sense.
is totally an artifact of, like, reinforcement by your brain.
That's what I'm saying.
I mean, then there's no right or wrong, right? Like, any of us can be either one. And you can change. Like, if you locked yourself in a room and forced yourself to write with the right pen for days at a time, you probably couldn't become
You
like,
also
super
would
right
kill
with it.
yourself.
Why did I have to lock the door?
Because you were committed to the bit.
I haven't done it.
I'm trying to teach Steven something about bit commitment here.
Yeah, I have problems.
Is this a metaphor or something?
No.
No.
It's a story I'll have to tell you later.
Steven wasn't committed enough to an extremely good bit.
How about those quinolines? I like creating a little bigger.
You just got to know the bit.
That makes them bigger.
It's almost as if we were trying to make a joke about that.
Here I was having the revelation of my job yesterday.
Why? What are you talking about?
Because how many people think of this stuff?
Construction workers?
I mean, chefs, electricians,
But you can like
plumbers,
Architects.
physicists, engineers.
You can see all of it.
You can also see the stuff we make. It's crystals in a vial.
Let them pass.
No moments will be had. This is a moment-free zone.
It's like pretty cool.
I agree.
Right.
I think everything we do is stupid until it makes it into music, and that's so much better.
What's going on? I just want to understand what's in your brains. Like, our stuff is cool that we do it because you can't see it. Actually, you can, you just like can't see it.
Like you build a table, whatever's not stuck, right? You can see like the screw in most people that always see the joints and how it's constructed with the molecule.
But you can't see like how the epoxy polymerized when you mix the two components of the epoxy. And yeah, I'm assembling my table with epoxy. Don't ask questions.
It's fine. Yeah, so like.
What about like growing cells on a plate? Like, you can't see what you're doing.
You're not like using like the.
Well, like that's kind of like a pretty good job, right? Like it's
Yeah, basically what you're saying is all jobs are slightly different from all other jobs, which I agree with.
but they're cooler because more cases of things.
Or-
If the thing is a secret.
but all jobs have subsets of those jobs that have hidden stuff. That's what I was getting at with carpentry and epoxy. Like,
Not art. In art, you can see all the
wait,
stuff,
so
art's the worst.
you're saying when you're a carpenter using epoxy, you're actually doing chemistry and not carpentry?
You're doing both.
I also do chemical reactions when I eat. Does that mean I'm working while I'm eating?
The coolest profession.
You are doing both.
Metabolizing.
Where the music comes Oh, that's right.
Oh,
It didn't break, it was just in. Alright.
stop at the beginning.
Oh, no, I meant
I like cancer.
No, I was like the director of the show.
Yeah, it's a lot. People lie.
Why would you lie? It was like we took our girls out in the desert and we were like, just want some water. And he said, well, like, me could drink out of this cactus, or if I can touch it, play it. It's probably going to make my hands fall down, but I can touch it.
What? Go to the hotel. Yeah.
But like, he literally knew that that was what was going to happen.
Maybe we can start 1 minute early. There won't be riots. Okay. Anybody need coffee? Okay. So today is a bit of a whirlwind. Today and tomorrow, we've got to cover a lot of stuff. Quinolines, isoquinolines, we're going to cover naphthyridines, we're going to cover crazy, bizarre radio labeling schemes. It's the 2 classes before the midterm. And then the midterm will be your worst nightmare. But you'll enjoy it. Okay, yeah, not many happy faces there. Okay, yeah. Anyway, so today, let's start with quinolines. And the way the lecture is sort of divided is by bond disconnections. And there is a chapter in the book on quinolines, and the chapter is pretty much like all of the others and goes through the starburst, the report card, the methods for substitution, and so we're going to try to distill it down to its essence here. We're also lucky to have a quinoline team to help us out in case we have issues. And I believe Vincent and Hannah are the quinoline team. So they already know everything here. And if I get stuck, they're going to help out. Okay, so these bond disconnections on quinoline are labeled in strategic order of the most popular to least popular. Most likely to be used to least likely. Okay? So there's your corner of strategery. But maybe before I begin, and since I started a minute early, it might be good to address 2 small things that Hannah and Nick brought to my attention yesterday that I don't want to confuse you with. The first is the selenium oxidation we saw of that C2 alkylated pyridine yesterday. In general, if you have a 2,5-dialkyl pyridine and you use selenium, selenium is going to be favoring oxidation of that methyl, or if there were a methyl at the 4 position, that one, because of the tautomeric form that exists in the ene-like mechanism. If you use something like CAMNO4, you're going to get oxidation generally everywhere. It's indiscriminate. So if you look in the literature, you'll find oxidation everywhere. If there's a competition between the 2, you'll often get a mixture, but it'll be favoring the CH bond that is more nucleophilic. So if you have a competition between these 2, it's likely you'll get a mixture favoring oxidation here over here. Didn't want to confuse you. You can't use selenium to oxidize everything. Okay? The other confusing thing to people was when we added that Grignard in the process problem. And people said, well, why doesn't the Grignard add into the electron withdrawing group? And the answer is, it is a reaction that is sporadically used. You won't use it ever for alkyl. It can be used for aryl, but it's best done when this position is blocked. And it usually will add here. But you often get mixtures. And so this is not a general reaction. It's one that the process chemists did on that exact example to see if they could skip some steps, and it worked. But it's not, please on the midterm or the exam, don't take electron withdrawing groups and just start adding Grignards everywhere. Okay, not a general reaction. Okay, but if you're a process chemist and you need to say, oh, well, could we use CH functionalization logic here and replace that CH bonds with just a direct addition? Something to consider. It's a possibility, but not something you want to go to every day. Does that clarify that? Okay, good. All right, so let's go back to quinolines. The disconnection A is the most popular one, and it's reasonable because it unravels the whole system to a ketone-like system with an amine. So if you unravel and disconnect A, the first thing you're going to get is a construct that looks like this. Which upon heating with acid, doesn't matter what the olefin geometry is, you will turn into a quinoline. You can also use equivalents of this. So if you want to use Chloroquine-like logic, you can do that too. You can do that and then reduce, and it'll cyclize. Okay, so that's disconnection A, very popular, because you can start from an ortho-halo aniline. So just like Chloroquine. But there are a number of ways of making quinolines that take advantage of innate reactivity of the neighboring arine. And so a lot of the disconnections we're going to talk about subsequently are doing just that. For example, one of the most popular ones and one of the oldest ones are corresponding to the name reaction set known as either the Combs or the Conrad-Limpak. And they're basically the same reaction, but one of them involves using pure alkyl systems, and one of them involves using one where you've got the ester on one side. And that disconnection looks something like that. Then a Friedel-Crafts takes over. So instead of putting a halogen atom here, you just take advantage of the fact that you're dealing with an electron-rich aromatic, and so you should be able to do Friedel-Crafts, right? Okay, that leads us to the diketone or dicarbonyl compound here, and a good example of this and the tunability of this reaction is shown in problem of the day number 1, where you can take aniline and this keto ester and just treat it gently at room temperature, let them sit together and cohabitate, and then heat it up with acid, or you can just immediately cook the thing up to 150 degrees with acid. And the product distribution is actually different. So for problem of the day number 1, we need someone to help rationalize what is what. Max, you look like you might want to tell us.
Yeah, sure. I don't want to talk through it or draw it out.
Well, I mean, either one. If you want to talk through it, I can draw what you tell me to draw.
Okay, so I guess we can start at the top row. So
Top row.
yeah, so at room temp, before adding acid, you probably condense onto the carbonyl first.
Which carbonyl?
Oh, the ketone carbonyl. Yeah, and then you add acid, and then you close up to make product. I guess A.
Okay, so you're going to go with A for that one, and then the other one.
For the other one, you probably make the amide, and then do have the aniline attack onto that ketone, and then use water to make product B.
So you can think of B. Good, great, Max. You can think of B as like a thermodynamic and an A as a kinetic. But the point to remember here is that when you have a dicarbonyl, if they are differentiated enough, and you use either these pseudo-kinetic or thermodynamic conditions, you can differentiate the regiochemistry. And this works pretty generally. You can find 100 examples of the Combs being, or the Conrad-Limpak being modulated depending on different electronic characteristics. If, however, your two R groups are pretty much the same electronically, you're out of luck. You're going to get mixtures. So, for example, this one here could be disconnected to the exact same logic. We can cut right down the middle. We start with aniline, and our ketone precursor would be, and because these are differentiated enough, you can get good regioselectivity. The top one being very much like, you can look at it as just ester-like if you want, and then the bottom one just being a regular ketone. And so the exact conditions for initiating this one are just heating with, mixing with acetic acid and then heating with acid. And they get, I think, a 67% yield of that product. If you have a case where, let's take a look at this one, where we're going to do the exact same disconnection down the middle. What could potentially be the problem with this case, Vincent? Do you foresee a problem?
No, because it's symmetric.
It's symmetric with regards to this, but what do you say there, Hannah?
The aniline's not symmetrical, so you can get regioisomersed where you're either ortho to the methyl or ortho on the other side.
And what do you think the major product's going to be?
Probably on the other side.
Yeah, in general, it goes away from the group. So in general, I mean, probably you're still, because the methyl's not very big, you're still going to get a little bit of the other regioisomer, but just like a Fischer indolization, you could predict it through sterics. Okay? And we'll see examples of this later as well. Let's take a look at another example in the context of making various antibiotics, the Gould-Jacobs reaction. So if we make the exact same disconnection we're eventually going to do this, but we'll do it stepwise. So you just mix those together, heat and some acid, and out pops the product. You can imagine addition, elimination, Frito Crafts, and you're good. These things are usually commercially available, but obviously easy to make from the corresponding malonate and triethyl orthoformate. The oldest way of making quinolines is what I think of as the witch's brew of heterocyclic chemistry. It's called the Skraup. Anybody ever done a Skraup? You done a Skraup? Did you like it?
No,
What color did it turn?
black.
Yeah. How did you get the product out?
It was a nightmare. I had to literally like crush up the goopy mixture with ethyl acetate to try and dissolve it. The yield was still only like 20%.
Yeah, that sounds like fun. So usually it takes aniline and glycerol, and you go through, and you have air, and you've got acid, and you can imagine anilines don't like air, nor do they like acid, so the black color is coming from that. And then the glycerol's got to do some redox change because it has to isomerize to something that can, look something like this. And this probably likes to polymerize a lot. That's not very happy. And so there's a trick to the Skraup. If you want to take your black tar and get out the product, you, at the end of the reaction, add zinc chloride. The quinoline will selectively make a 2-to-1 complex with the zinc. And then you can separate that from the black tar and then decomplex when you're done. The yield is often better doing it that way. There's also more modern variants of the Skraup that will, instead of using aniline, use a better nucleophile like tosyl aniline and a better Michael acceptor, for instance, acrylonitrile. And we're going to see an example of that later. So Skraup equivalents exist, and to this day, you will still sometimes see people use the regular old Skraup. Sometimes the yields are really high, I have to say. You see these JMed Chem yields are like 80%. So sometimes it works. And a trick to isolating is use that zinc trick. Questions? Okay. Let's look what happens when we disconnect A and C. That gets us to a disconnection that looks like that. This is known as the Friedländer reaction. So it involves the union of a ketoaniline and another ketone, and you treat it with base. For example, if we use this disconnection of A and C on this one, our building block would be what? Steve, what is my building block? On the left is going to be and on the right, great. Treat these with sodium methoxide in 50 degrees. Friedländer takes place, and you get your quinoline. Happy? Okay. Problem with idea number 2. And looks like second row Max has volunteered, thank you so much, for problem with idea number 2. So they're going to pass the iPad over to you. And I'll just copy, dutifully, whatever you tell me to copy.
Oh, this is going to take a while.
You think so?
Well, if I don't draw all the resonance structures, maybe
Yes, you can abbreviate. We don't need all the resonance structures.
Okay.
So it involves taking the keto acid here, and we're going to boil it 95 degrees. We're going to add a little KOH. That's kind of important.
Okay, so I condense onto that photodiag. Why did I do that? Yeah, and then hydrolyze that.
You're going to hydrolyze that? Okay, let's hydrolyze that first and see what that gives us. All right, great. can't really see what you got here. Is what you have here the same as what I've drawn? The hydrolysis product? Is that what you drew?
No.
What did you draw?
I drew it condensing onto the ketone first.
Aha.
Do the opposite.
Aha. So this is known as the Fitzinger reaction, and when you said you hydrolyze, you want to do the hydrolysis first with the KOH. So the KOH takes care of the isoten, opens it up, and then you do your condensation.
Okay, then condense them. And then after that, just condense the methyl.
Yeah. So Fitzinger, great. Thanks, Max. So Fitzinger is nothing more than a hiding Friedländer. So there's Friedländer. Here's Friedländer. Look at the Friedländer and look at the Fitzinger. The only difference is that my R group here, instead of being an aldehyde in that case, my R group was a CO2H. What's confusing about these reactions and mechanisms is that you see all the free acids and you're like, wait a minute, is it going to deprotonate? How does it do that? Remember, you're at KOH, you're at 100 degrees, you're equilibrating, and the thermodynamic product is always these heterocycles. So although you may have other deprotonation states, don't let it confuse you. Fitzinger you see quite often. We'll see it again today. So try to remember it.
In practice, do people prefer to do it that way as opposed to using like a arylaldehyde?
They prefer the arylhaldehyde because you have to make an isoten.
And that's harder.
It's more steps. Often the aldehyde can be either obtained from Aldrich or you can just make it through lithiation DMF. The other thing is, remember, this doesn't need to be an aldehyde. That can be phenyl, aryl, pyridyl, whatever. It can be something crazy, big.
So then when do people use the isosten over that?
When it's strategically easy to, usually they're going to do it when they have a signaling element with these two rings here, with these two substituents here. Or if they have the isoten in hand. We'll see an example where they do exactly this in favor of a Friedländer. So stay tuned for that case study. Okay, A plus B plus D is what you do when Fitzinger doesn't work. So for instance, when R is equal to T-butyl, you can make this compound through decarboxylation. Just heat this thing up with copper, quinoline, whatever your favorite decarboxylation conditions are. Because it's the C4 position of the quinoline, it decarboxylates well. If R is equal to T-butyl, then you need to use another type of reaction. And if we're going to disconnect A plus B plus D, think for a moment what that might look like.
Looks like an aldehyde and a methyl ketone or something.
So we're going to have our aniline, right? Let's just put T-butyl for, there's your aldehyde. And then there's a ketone. Perfect. Dobner. I think this is called Dobner. Yes, this is a Dobner, and it works when Fitzinger fails. Great. So problem today number 3 is one that should be super easy for you. Probably easy for Steve. Problem today number 3. There it is. Use disconnections B plus C and propose the synthesis of chloroquinoline.
Talk you through it as opposed to writing.
If it's easy enough for you to talk through, I'll happily just be your chalk slave and put whatever you want there.
Okay. So cut it back to the. Yes, you can cut that out, and then also cut the N carbon bond with the one that's bound to the chloride.
Well, first let's do B and C. I need an intermediate here, so I don't go too fast. Tell me what intermediate you want.
Draw the like Vilsmeier at
Aha! And where did that thing come from?
And then that came from if you cut the imine back to the aldehyde.
Well, this came from the Vilsmeier reaction.
Yeah.
So, and the chloro obviously also came from the Vilsmeier. So what's my starting material?
Oh, okay. But yeah, amide. Oh, okay, I see. Like, long oxidative state.
This is the meth cone. But there's no need to memorize any of that nonsense. Just remember it's the Vilsmeier approach. We've seen the Vilsmeier now a few times. A few different heterocycles we can make through Vilsmeier approach. You can make a lot of heterocycles to that. Super nice because it's a free carbon atom. And it's a free diversification. So you can Suzuki your heart out on that. Or Buckwall, whatever you like. Questions? Okay, great. Let's look at disconnection D. What do you suspect are the possible products of disconnection D? So you take just a simple, you can imagine this is an easy compound to make through either lithiation, quench with the acid chloride, or if you're lucky and the substituents are right, maybe a Friedländer will give you that directly. Tons of ways of making that. But when I treat this with base, there are two possible things that can form. And there's your clue. They both have that skeleton. And probably still retain the nitrogen. So let's draw that too.
Basically deprotonate either on the N-acetyl or on the methyl ketone.
So if I deprotonate here, I get that one. If I deprotonate here, I get that one. Is that what you're saying, Saul?
That is what I'm saying.
That is what you're saying.
Yes.
And what do you think is the major product of that reaction?
I'm going to guess the first drawn because ketones are more acidic and the NH should protect you somewhat from deprotonation.
But once you deprotonate that NH, don't you think there's going to be an issue with the difficulty in attacking that carbonyl?
Sure. So I guess I'm going to say all of this is under thermodynamic control, and the amide is probably thermodynamically favorable.
It's, I think, 80-20, something like that, favoring that as the major. So this disconnection is not a great disconnection when you've got this type of amide system in play. And the so-called Camp's reaction is best used when, let's say, instead of methyl, it was phenyl. Then there's no choice of where it's going to go.
Can you just stick an R group on the nitrogen to fix this reaction?
Yeah, you could put if you put an N-benzyl AC, sure. Then you would, unfortunately, still get a mixture. You're still going to get a mixture. It won't be pure. That's the problem. It won't be pure. So if you want to get regiochemical certainty, make one component non-utilizable, and then you're guaranteed to only get one. There's no uncertainty at all. No mixture. But what Saul says is a good idea for accentuating, maybe getting even more of this guy. Okay. E, disconnection E. This is to make cipro. If you look at the front page of your handout, probably many of you have taken cipro at one point in your life. It's a pretty standard antibiotic. So if you've got a system where this is more rare, just because, as you can imagine, you need to have either SNARable substrate or the right halogen arrangement so you can do a palladium amination. And the product of this is as you would expect.
Why does the SNIR go with that regiochemistry? I would have expected it to go to the parachloral.
Because it's intramolecularly driven.
Oh, it does the addition first.
Exactly. Great question. Everybody see that? Yep. All right. We can't have a discussion about quinolines without at least teasing you a little bit with a radiochemical question. So here's an example straight out of the literature. And this one is going to be N15 labeled. So we're happy to take suggestions from the Quinoline team or anyone who would like to contribute. Any thoughts on what might be a good strategy are certainly welcome. Any ways of thinking about this?
What about we disconnect this to the 4-quinolone and then make a very similar disconnection to what we did for cipro?
Oh, how do I make that?
So you can cut, according to our nomenclature, bonds E and A.
Okay. Everybody happy with that one? Max, are you happy with it?
Well, I was just looking at, you haven't talked about it yet, but disconnect B and E to the box below where we're at right now. Looks like pretty nice because you can just feed it enriched ammonia. So if you just take that substrate down there and just draw on the appropriate substituents, like that dialdehyde.
Well, it's not a dialdehyde. It's there's going to be.
Sorry, yeah.
So that's you favor this one, disconnection A.
Oh no, I was saying
That makes an isoquinoline.
That's for isoquinoline.
oh, right, sorry.
But what you mean? What I just drew is A. That's what you meant. That's what you just said.
Yeah, sure thing.
It's A.
I guess if you put a chloro there, then you could just do the Friedländer at the end.
If you put a chloro there, sorry.
Take Max's idea, and then instead of making the aryl N, just do aryl chloride there, and then maybe you could condense N15 and do an intramolecular, or sorry, not Friedländer, SNAR.
With a permethoxy.
You mean this?
Yeah.
And then do some sort of Buchwald in your ammonia labeled ammonia source. You know, yeah.
Take this pyridone and disconnect E and A. And then
Disconnect B and A.
E and A
E and A.
from pyridone.
That's this.
No, or the fluor or acetylene.
Uh-huh. Oh, okay.
And then kind of alkyne or like cipro, like methoxyalkene,
And then
treated with labeled ammonia.
like this.
Correct.
Okay, so the issue I would have with this one, just to tell you, all of these are fine on the midterm. You put something like this, we can't mark it off, okay? It's fine. This one might give you regiochemical problems, and you're dealing with, I'm not sure if N15 is a stable label, so I don't think I don't think it would be a problem to have, but still, the companies are still kind of rigorous about having any kind of labeled thing. So you need a separate weight stream. You may have a mixture of regioisomers here, depending on the conditions. Then you've got to do a PLCl3 step and then reduce it down, so it's more steps. This one, there's nothing wrong with it. This one, I got to do a decarboxylation, and I got to do POCl3, palladium. The way they ended up actually doing this was just from a Friedländer. The nitrogen can be incorporated by using a Buchwald type reaction. And then base. That's the way they did it. Questions? All right, isoquinolines. Let's see how we make them. Again, the disconnections are labeled in order of what you're going to see in the real world. And so let's go through the most popular one, which is AB. It's the one that's most intuitive to all of you. Probably you've seen it multiple times in the course of your studies. And it involves a simple event that I won't tell you yet, but if X is equal to H, it's known as Bischler-Nipralski. And if X is equal to some sort of leaving group, let's say OH, it's known as a Pictet GAMS. If it's H, it's Pictet GAMS, it's OH, yes. It was the golden age to be in the Pictet group, right? If you were GAMS or Hubert or Spengler, or there's a few others, your name is sort of emblazoned forever. The good old days. Okay, so what's the intermediate you would use here for Bischler-Nipralski or the Pictet GAMS? Dongmin, what do I put here?
Maybe an amide.
Now, if I take the amine and I make the amide, and then treat that with some acid or POCl3, but this is made from the corresponding amine, so the net overall process is disconnecting there and there. And one can do that with this present or not. If it's not present, you need to oxidize. You can do this on biaryl systems. So for instance, this acid analyte. Zinc chloride gives you a phenanthrene. Same thing, but different type of heterocycle, so we get a different name for it. Don't need to memorize this stuff, though. Disconnection D is a problem of the day that we need a volunteer for. And luckily, Zhang has volunteered.
That's it.
Just FYI, I want to give fair warning. We're going to need the help of Florida for problem of the day number 5. So please prepare yourselves. So Zhang, what do I do here? I'm going to watch and then copy whatever you tell me.
Thinking it probably actualizes or opens up the lactam.
Okay, you draw that and I'll copy. All right, that looks good. Now what do I do?
Oh, and then you just deprotonate here.
Okay.
And then that's it.
That sounds good. Hey, Zheng, for the extra bonus points, can you come up with another possible mechanism? Like, I'll give you a clue. What if you just reverse the order of what you just did? Would there be a way to get to the product?
Oh, deprotonate first.
Just let's play a game and see what happens. If you were to deprotonate first, what could you do to get to the product, hypothetically?
Let's see.
Ziridians are chumps.
Thanks all.
Great. And then after you get that product, how could you possibly get to the final adduct?
Let's see.
Maybe it's a dead end, but let's just see. Let's just see if you can do it. Can we get there, or maybe not?
Guess then you can.
Yeah. Great. You'll see both of these mechanisms in the literature. I mean, we looked a few years back, and apparently this is not necessarily violating any Baldwin standards, but it's known as the Gabriel-Coleman rearrangement. For ease, you can think of it as a hydrolysis followed by the condensation, okay? But if you see in the literature the cyclopropane intermediate or the Ziridine intermediate, you don't have to curse me and say he never showed us that, okay? It exists. B plus C is known as the Pomeranz-Fritsch, and it is pretty straightforward, as you can imagine. You just treat this with acid, and you get out the product by a simple Friedel-Crafts. Starts from a benzylamine. A benzaldehyde plus a simple amine, which we will see over and over again in this class.
If you need to make substituted versions of that, like, is there a quick way to
Tell me what you want.
alpha aminate and aldehyde, like equivalent oxidation state to that, or a ketone?
Yeah. So, and this space has been reserved specifically for Saul's question because we anticipated it. So, you can take these types of species and you can treat them with certain types of halogenating agents, and they will fleetingly go through the intermediacy of these. You can put chloro or bromo there, and then you can add an amine. So certain halogenating agents are known to do this, like the pyridinium trihydrobromides will do this. There's a few out there. So that's how you would make the substituted version. Great question. And then B plus E you rarely see, because obviously dialdehydes are a pain. Hard to make these. But if you have that dialdehyde in hand, and you hook it up with ammonia, you'll get out the isoquinoline, sorry. If you cook it up with hydroxylamine, you'll get the isoquinoline N oxide. And if you cook it up with the RNH2, you'll get the isoquinolonium salt. Okay? With that, we can move on to case studies. So let's talk about the first one, chloroquine. And it's just an example of the power of medicinal chemistry, that chloroquine and various versions of this are now widely used as antimalarials. They have been for many years. People still get chloroquine and derivatives of them for treating malaria in certain parts of the world. And before the invention of these compounds in the 40s, the treatment for this for malaria was a spider wrapped in molasses. Don't know if it was a placebo effect or what, but as you can imagine, malaria was a big problem until the spiders were replaced with chloroquine. But that's a true story. Okay, so the synthesis of chloroquine begins with simple aniline, and we treat this with a tricarbonyl. So, need help figuring out what goes on here. I've got an intermediate that forms, and then I heat it up. So what might be the most likely carbonyl to react just at 40 degrees in acetic acid? Sorry, which one?
I said ketone on the aniline too.
So switch the screens. Can't see the board.
Great. And then when I heat this thing up, awesome. And then when I treat this with base, followed by POCl3, let's look at the front page of the handout. Let's look at the structure of the final product. Chloroquine. There it is.
Decarboxylate.
Okay, we'll need to do that. So KOH and heat is going to lop this fella off. And then POCl3.
Make methyl chloride.
And then we add in our amine, and we get chloroquine. Super. There's a modern variant of this, and it is a Skraup equivalent. So if you take this dichloroaniline in the context of a different molecule in the series, and you react it with acrylonitrile, you get clean Michael addition. KOH then hydrolyzes the nitrile to the acid, and then treating that with acid gives you your same type of adduct.
It's like Skraup Plus.
It's like Skraup Plus. Palladium on carbon and POCl3. What's the palladium on carbon do, Jess?
Just the
When you see palladium and carbon, your knee-jerk response is to reduce something, isn't it? But I didn't put any hydrogen there. So if there's no hydrogen, here's a trick. If you see palladium on carbon and there's no hydrogen there, you're going to get it from somewhere. It's not from the atmosphere. There's not a lot of H2 in the atmosphere. So the only one other choice for your H2 is going to be from Yeah, so exactly. So you're going to get it from your substrate, and that's going to dehydrogenate it here. And then PlCl3 will do exactly what Sol taught us in the previous problem to give you that.
Are those reactions stoichiometric in theory?
No.
They have all hydrogen.
Okay, how about some radio fun? Using the same exact logic, how would we give me some disconnections for that? What do you say, Chang? Some thoughts on how to radio label at that carbon, C14?
Chlorine makes me want to just burst out shit.
It certainly might want you to do that, make you want to do that, but and you can certainly try, but the location of the Vilsmeier might be problematic. You got a cheat sheet right over there. Bunch of disconnections you can use.
So maybe I'll disconnect A and B.
Something like this. Make the amide bond here first and cyclize. And then you're going to have to make that. I mean, if you made this radiolabeled, you have a way to get the free acid there. You do the amide bond formation, and then you do the Friedel-Crafts. There's another problem that we don't want a carbonyl there, so we need to switch this up. Sorry. This should be labeled here, then we're fine. We'll do the addition here, and then we'll do Friedel-Crafts. That's what you wanted, right? Sorry. Now we just need to make this compound radiolabeled.
Vinyl bromide carbon dioxide.
So hypothetically, I guess one could make that, and then add it to labeled CO2. Okay. I mean, if you put that in a test, you can't mark it wrong. It's not bad. I don't think it's bad. Any other ideas?
Labeled acetic acid and ortho.
Labeled acetic acid. Oh, do you mean to make this? Sure. Okay. Any other ideas?
If we start from the acetyl-aniline,
And do what?
I'm going to attempt to use some labeled DMF to condense onto what's formally like a equivalent of formal. So that's going to be H, disconnecting that bond. And the thought is to use a very similar disconnection to what's listed from the day number 3 at the top of the same board. But it's easy to compare it off of. Right, so you make hot Vilsmeier.
But then you're going to have to put a chloro in there at the end. How are you going to get that chloro in there? You got it here at the wrong
It's in the
spot.
wrong position, yeah.
Maybe we have ester where H is, and that would be labeled from, say, trapping with CO2, and then treat that. I don't want to ask.
Treat it with base or something. But then you've got...
But that's from, say, that instead of getting the acetate, say, throw in acetaldehyde.
I see. This type of disconnection. And heat that up.
Yeah.
The problem is acetaldehyde and base is largely going to give you a mixture of misery.
Friedländer type, what I mean, sorry, guys.
Can you what?
Friedländer.
So a Friedländer disconnection would require aldehyde here. We're going to label our aldehyde, I assume. Plus, then you need some very simple, it's sort of the same disconnection that Tucker just said.
And then test all the other things.
Oh, here. Okay. Then decarboxylate and then POCl3. Sure. That would work. You just need to decarboxylate. And, the other problem is you got to put the chlorine in. How are you going to put that chlorine in?
Can we do Friedländer type not from aldehydes but from acids?
So you want to put an ester here and then treat that one with base.
I don't know.
Perhaps, maybe if you use methoxide, that might be known. That's probably known. All of these ideas are reasonable. On the other hand, one could just take the exact same thing we saw here. Could just take this and make that labeled. So you could just take vinyl magnesium bromide, quench your CO2, take the acrylate, do a Michael addition, and then acid, and then POCl3, and you'd be done. That's the way they ended up doing it. But these ideas are not so bad. I mean, some of them are going to have some issue, but this one in particular is okay.
Hey, Phil,
Yes.
do people use labeled cyanide as a nucleophile for displacing
time.
halides?
All the time. So, but you can't displace a vinyl bromide to a vinyl to make a acrylonitrile. But you could take an aromatic ring that's got an arobromide on it, use palladium, and labeled sodium cyanide. Is that the question?
Yeah, I mean, I was thinking, so the third to last intermediate with the tethered nitrile off the aryl ring.
This one right
you
here.
Just,
This one right here.
yeah, you just make that with labeled cyanide.
Oh, I see what you're saying. So you want to do like a mustard X here.
Sure.
React that with a dihaloethane followed by sodium cyanide. There's nothing wrong with that. It's a good idea. Great. Yeah. Thanks, Alex. Any other questions? Okay. Well, now we're going to move to a cage match between E.J. Corey and Steve Weinreb. And they're going to be competing on routes to coenzyme PQQ, also known as methoxetin, the structure of which is shown here. And here we have embedded within the same structure, there's a pyrrole or indole, however you want to look at it, hiding on a pyridine or a quinoline, however you want to look at it. Whoever gets to use that aromatic ring either becomes the pyridine or the quinoline or the indole. So how do you disconnect this? Well, the two are relatively equal in priority based on the substituents and the logic involved. And so this is a case where you could imagine breaking A or breaking C on a nucleus of B. And so we're going to see today in the first synthesis how Corey starts with A and builds on C, or the disconnection goes from A to C versus Weinreb, who goes from C to A, retrosynthetically. Okay, so let's begin with the Corey synthesis. So the Corey synthesis first starts with formic acid, acetic anhydride, which is a nice mixture for taking anilines or amines and turning them into something.
Depends on the hindrance. They usually form amides.
Okay, thanks, Saul. So you make the formamide, followed by reduction of the nitro to the aniline. Then we take this aniline and we treat it with sodium nitrate.
Exposed to benzene.
And that will convert this into a diazonium salt. And then a name reaction takes place from lecture number maybe 6 or 5. Jap Klingman. And then we treat this with acid, and it does another name reaction. Fischer. And we have our indole. So the strategy here is let's build an indole first, and then we're going to have to annulate onto that our quinoline. So the first step of doing that is HCl and heat, which is going to effectively remove this labile protecting group, the formamide, departs, and in its wake you have the aniline. And then the aniline is going to react with this compound by the same thing we just saw over there. And now we have our indole, or pyrrole, connected to a quinoline, or pyridine, however you want to think about it. And then to finish this, all you have to do is oxidative manipulations. And then hydrolyze the esters. And you're done. So Weinreb takes a completely different tack, and he starts off with Florida's problem of the day, number 5. And we have covered this a little bit, but we didn't really go through the details. Tried to save it for today. So we start off with the...
Missing a carbon.
Oh, am I missing a... Oh, it's not... Yeah. Yeah, if you look at the problem today, it's written correctly on the paper. So, yeah. But the Floridians have figured that out. So, Alex and folks over there, why don't you tell me what to do? We can hear you.
I guess first you would condense with the chloroacetaldehyde.
With what? The chloral reacts with what?
I think both the amine and ortho to it, because you need to introduce 2 more carbons.
Is there a reason for the hydroxylamine?
I'm sure. Like maybe that condenses with chloral.
You know, I think the problem with the what is known as the Sandmeyer isotope synthesis is that it's confusing to students because there's so many nucleophiles and possible electrophiles, and so the mechanism can be fairly nebulous because you can get to the product by doing what Alex said. So hypothetically, if we just were to make an intermediate like he said, for instance, something like this, I think you can meander your way to the product from this somehow by doing, oxidation shifts, but it's not so clean. So instead, Alex, why don't we start off with thinking about what the hydroxylamine does as the most potent nucleophile in there to begin with, instead of the aniline. And so if we take chloral and react it with hydroxylamine, what do you think happens?
You could displace a chloride first. Or
That's the
condense with
confusing
chlor-
thing, right? You could imagine doing that. But instead, this is a very electrophilic carbonyl. So instead,
Chloroquine.
we'll make the hydroxylamine adduct. Now, you may be tempted to take this nucleophile and immediately add it to here and lose a chlorine. You may be tempted to do that. Are you tempted, Alex?
Not anymore.
Not anymore. But he was, and I bet many people here were also tempted to do that. So as it turns out, this is a tricky problem. As it turns out, this will do this. Now, this compound, we can do exactly what you had the temptation to do, Alex. So instead of adding at that intermediate, we're going to divert it and instead add it here. Giving us this intermediate. And under these conditions, as you can imagine, a carbon atom bearing 2 chlorines and a nitrogen is going to rapidly want to do that. Not once, but twice. And so the final product of this problem of the day is that. This is the Sandmeyer isotin synthesis. It's not an isotin yet. I need to treat it with PPA, don't I? And once I treat this thing with PPA, I will lose water, and what will pop out with the right substituents here is my isotin. People don't like to use this reaction in industry so much because chloral is a very dangerous, it's a somewhat regulated substance. It's pretty toxic. There's a number of problems with it apparently, but you can still order it, I believe. Anyway, now we have an isotin, and now we're set up for a reaction we learned all the way many ages ago on the other half of that board. Which one is it, Steve? It is a named reaction, indeed. And that named reaction, we did it even, I thought you even did it in a problem of the day.
Fitzinger.
Okay, Fitzinger, and the Fitzinger is going to give us, after Fischer esterification, you'll note there's a methanol H plus step there, that. Now, NBS under radical conditions is going to brominate benzylically. Nitration is going to nitrate here, and then this will be alkylated by this dicarbonyl.
And nitration makes sense to you.
We got this question last year as well, and the regiochemistry perhaps can be rationalized by a protonation that takes place here, perhaps avoiding nitration here and favoring over there. That's the best I can come up with. And then we're going to do what Saul taught us just a minute ago, which is to treat this with KOH and the diazonium, which is going to give us a Jap-Klingman product. Followed by palladium on carbon. And this time we've got some hydrogen in there. And so before I draw the product, I just wanted to show you what happened here. When you reduce, so the Jap Klingman just gave us the hydrazone. Essentially, just oxidized that carbon. You see that? This intermediate hydrazine, we're not going to do free fissures or anything like that. Once we have the amine here, after palladium on carbon reduces that nitro group to the amine, this then snaps shut to give us the same indol that Corey made. And once we're in this territory, we can do oxidation stuff and lithium hydroxide, and we get the product. Which route do you like better? Gigi, what do you like better?
Maybe I prefer the Corey one.
Because you think he's going to watch the video? Because you're a Corey grandchild? Or what? Is there any specific reason you like it better?
Probably I think it's more straightforward to me. I'm not sure.
Okay. It's a toss-up. I mean, if we were to do it's really an opinion-based thing. I can't say that one is better than the other. They're great for this class, I'll tell you that. Thank goodness they both did this, or I would be in big trouble today. It's really perfect for this class, seeing that these two different disconnections, and they're both pretty much equivalent. Can't really say, you'd have to really get into the weeds as a process chemist and analyze the whole thing to say, okay, this one's better for making kilos. Okay, great. Problem of the day number 6 is sort of trying to encapsulate, we're trying to cover in problem of the day number 6 many thousands of papers in one or 2 minutes. So these alkaloids, there's a lot of these natural products that exist out there, these tetrahydro isoquinoline alkaloids. There's a lot of them out there. And problem of the day number 6 asks a simple question, can you come up with 2 ways of making it? One of them through ring synthesis and one of them through ring substitution.
How about we start from a benzoyl ketone and phenethylamine? We do reductive.
So Saul says, how about we start from a benzylic ketone you mean this kind of benzylic ketone?
Exactly the benzoyl ketone that I mean.
Okay. And then do what?
And a phenethylamine. So it's already diluted.
And where does this thing come from?
I'm not that far ahead yet. Trio cross isolation should go to that position. And then I basically made dopa.
So dopamine derivative, or dopamine itself. So Saul dips into the phenethylamines I have known and loved book to find out the preparation. And then does a Friedel Crafts followed by snapping shut. How do you install the stereo center?
You didn't tell me you wanted it not racemic.
I mean, you can make it racemic if you want. It's up to you. But I'm just asking, how would you make it an anti-pure? You could use auxiliaries, perhaps. Any other ways? Yeah. Asymmetric hydrogenation would be a really quick way to do it. Any other thoughts here?
Pick that Spangler from that same intermediate.
I think that Spangler looks great. And so actually the same reaction scheme. We're just taking Saul's exact disconnection, and instead of trying to do a Friedel Crafts, just make the amide bond and then treat a POCl3. That's probably what would happen. It's probably easier to do what Tucker just said, because you just take, you don't need any R here, just the amine directly, make the amide, and then Bishop-Niporalski to the closure. Yes?
Can we treat it with Alden?
Treat which with the aldehyde, sorry?
Instead of isochloride, take aldehyde.
Yeah, so take the aldehyde and then maybe some asymmetric Pickett-Spengler type reaction. Sure. Some chirobronzed acid, perhaps, would give you the direct product. Yeah, why not? You don't like it? I mean, it's fine on paper. Sure. There's nothing wrong with it. Okay, so that's basically the ring synthesis. Is there a way we learned from lecture 2 or 3 on how to make this through ring substitution?
Dehydrogenation of acetyl. You should definitely reduce the heteroaromatic ring before you reduce that super electron-rich area.
Yeah, that's one way. Sure, I bet there's some modern reduction technology that would get you to that, maybe even asymmetrically. Sure. Any other ring substitution methods? Maybe from the isoquinoline itself, not bearing the methylene alcohol? Reiser reaction sounds awesome. So we could take the corresponding quinoline here, and when we treat the quinoline under Reiser conditions, benzoyl chloride and some cyanide source, you're going to get out that. I think even Shibasaki published many years ago an asymmetric Reiser reaction. And then full reduction and you're done. So ring synthesis, substitution, either one will get you there. Okay, in the final 10 or 15 minutes here, we'll go through Camptothecin. It's a natural product that has been made dozens of times. On the back of your handout is a clipping from a tetrahedron review in which they outline a lot of the syntheses of Camptothecin. Even the Boga group has a great synthesis of Camptothecin. Don't worry, Gigi, I won't quiz you on it. But we'll cover 3 just highlights of them today. The first one is Stork, the next one will be Danishevsky, and the final one will be Corey. Then we'll get to the Pfizer problem, and we will be done for today. So Camptothecin begins with a named reaction from Stork. We learned it 100 times already. Just a Friedländer, right? Can you rationalize for me, someone, the regiochemistry? Steve, any thoughts why it went there? I mean, in theory, I could go either here or here.
I guess it's just more acidic position.
It's probably a mixture of acidity and just sterics. Yeah, the other one's going to be a little bit more challenging to deprotonate. And if you did deprotonate it, let's say you did, it's reversible. Right? So the retroaldol would happen really quick, whereas the other one would lose water and you're not going back from there. Okay, great. So he takes this compound and he traverses a few steps to annulate on the quinolone, and then he treats this with LDA and this interesting acceptor in what is a very, it's probably one of the first examples of a now a process that we take for granted as being rather commonplace. Tucker, can you tell us what the first step is?
Deprotonate.
What?
The phenolphus on the amide.
Deprotonate here?
Yes.
Okay, now what do I do? And a good hint, by the way, would be to look at the front page of the handout to see what Camptothecin actually looks like. Any other places I can deprotonate? Because deprotoning there leads to a substitution pattern which is not necessarily found in Camptothecin, is it?
Correct.
Correct. Okay. So why don't we look for another spot to deprotonate? Are there any other spots?
On the other piece, yeah, at the alpha position there. And that's going to add in 1, 4.
Okay. And then the resulting enolate would then add in where?
The carbonate is yet.
Great.
Thanks for the slow-mo.
Yep. And so let's draw it out. We've got E here. We've got OH here. We've got ethyl. Oh, it's not OH. We've got. Let's make it easy. There we go. And then there. That looks a lot like Camptothecin now, and this is a very early example of what is now known as a vicinal difunctionalization. We take this for granted now, but back when LDA was all the rage, and LDA used to be CH activation of the day, right? It was a big deal. Okay, so we treat this with HCl, and then borohydride, and then acetic anhydride, and then DDQ. So the HCl is going to take our ester and convert it into an acid. The borohydride is going to take our lactone and turn it into an acetate. Lactone to lactol, followed by acetate. And then DDQ is going to oxidize us all the way up. And now take a look at the front page of your handout. Look at the structure of Camptothecin. And imagine what we need to do to finish. What do we need to do to finish? Would be sodium hydroxide is going to cleave that acetate. Borohydride is going to reduce this to the benzyl alcohol, so that bond is going to cleave. And then H plus is going to is just going to lactonize this alcohol, goes on here. Let's look at the front page of the handout. Let's check Camptothecin. Do we have it right? Oh, yes. There it is. Does everybody see that? Look at Camptothecin. Look what I just did. Great. Problem of the day number 7. It's the only step of Daniszewski synthesis we will cover. It's a new way of making this type of heterocycle. And it's a relatively straightforward problem of the day. So one can call it out, or you can draw it. Any takers for this one? So what do you say, Max?
That is enamine attack alley.
So sorry, I forgot where it attacks. Can you help me?
At the alley.
Is that adduct right?
Yeah, basically arrows. Yeah.
Basically what?
Basically arrows. Yes.
Okay. Now what do I do?
Well, you have to grab that proton from somewhere.
Which proton? This one?
Yeah.
Okay, I've grabbed it.
I guess then you can push that back onto nitrogen, and then subsequently onto. Okay, you're gonna go around. Okay. One for addition, right? Oh, no, this is the ester. Yeah.
Okay, great. And that gives us,
So you traced out the answer in your arrow too.
what's that?
You traced out the answer in your arrow.
I did?
You just wrote lowercase e.
Oh, yeah. Oh, yeah, that's right. And then an annulation takes place here, and he finishes the synthesis. Let me make sure I have the right 1, 2, 3, 1, 2, 3, sorry. And if you want, you can trace out in your head what that looks like on Camptothecin. All right, we're doing good on time. And the last synthesis of Camptothecin we will cover is very briefly the Cori one. This is the key step. And requires you know something about basic reactivity of quinolines. It's a very bizarre-looking problem, but hopefully we get some help from someone. So we take this quinoline bearing an amine, and we couple it with this strange-looking creature with pyridine. Then there's a sodium acetate step, and then finally a sodium mercaptan step. Vince, any ideas on the first step? I got some electrophiles here, don't I? Let's identify all the electrophiles.
All the chemicals.
Okay. And is there another electrophile?
The carbon complex.
Huh. If you had to give sort of an order, or you think of reactivity, which one might be 1 and 2, or the highest?
2 might be the most.
A carbonate.
I guess not.
Okay.
1 then?
1 is pretty good. So if we react this directly with this, it will then open up, expel HCl, and the adduct we will get looks like this. Okay, great. So while I was drawing this out, now someone hopefully figured out what's going on with sodium acetate and acetic acid. Take a look at the structure of Camptothecin if that helps you.
The benzoic position of the quinoline is super acidic.
The benzylic position of the quinoline is superacidic. You mean this one?
No, I mean the other one.
Why is the other one better?
It's like an E.
So we do our aldol, and then you deprotect this carbonate by the sulfur adding in SN2 prime fashion to the methyl, expelling the carbonate, losing CO2. And you're done. That's problem today number 8. How do you make this species here? Any suggestions?
Which one items are you putting?
The starting amine. What, Friedländer? Plus this? You worried about regiochemistry problems?
No, I think it should be fine.
Yeah, you probably would get that as a major product. I agree. That's not how we did it. Turns out this is cheap as chips. You can ozonalize this to the dialdehyde selectively. Stops. And then reductive amination. But nothing wrong with proposing a Friedländer. Like that too. Great. That leaves us exactly 3 minutes for Patrick's problem on this quinoline. And so we have not covered this heterocycle before.
Sorry.
That's okay. And so it is a benzannulated pyrimidine. I won't go into what it's called, but let's just call it a pyrimidine. We're going to focus on the pyrimidine. And if you want to vary R1 and R2, it would appear that what we need there are 2 halogens that are differentially reactive. And so the first assumption we can make is that this compound, before we even get into how we synthesize anything, and this could be bromo if you want, but I would suggest chloro. This should have differential reactivity wherein this one reacts first, followed by this one. Would you agree? In standard palladium couplings. So all we need to do is come up with a synthesis of that. And so what one could do, as we will learn when we talk about pyrimidines, it's basically just 1,3-dicarbonyl logic. So formamidine acetate, boil that up with this, we'll give you this, followed by PLCl3, we'll give you this. If you don't want to do the PLCl3 step, the advantage is, at the paper we talked about at lecture 1, you could also take the OH and do direct couplings with that using PIBOP, or you could do direct Suzuki as well. Remember, I think we gave you or read in that paper. So you don't need to go to the PLC3 step if you want, because the OH there will be through the HOAT adduct, will be more reactive than the chloro. This is going to be dead on arrival until you're ready to soup it up with a stronger ligand. Is that good enough, or are you already not good?
We're having some problems with the chloro at the
The chloro here is not reactive.
yeah, it's not reactive.
And what do you want to put there? Amines and alkyl groups and aryls?
Yeah, and then also some making ethers. Try some Chandler stuff.
Chanlam with a boronic acid here, you mean?
Or, yeah, sorry.
Can you adjust the
So
camera,
you can make the
please?
boronic acid there as well. And it's still not reactive enough. Have you made the triplet there? Because you could use the exact same logic with OR here. And then when you're done putting diversity here, convert the OR into O-triplet and then have at it. Might be even more reactive. If you put iodide or bromide, we're going to have a problem with cross-reactivity here. So maybe an OR. The problem with CH activation is there's no good way to direct it here on a heterocycle of this type because of competing reactivity here and the other spots with iridium. So for late stage, probably trying a triflate there would be one recommendation, but we can open it up to anyone else. But the thing to remember in this class here is that when we cover pyrimidines, we're going to be thinking about 1,3 dicarbonyl logic, where the carbonyls are essentially there. And this would be known as the 3+3 annulation, but we're not covering that until after the midterm. So nothing I'm talking about here is something you need to recall until after the midterm. Is that useful, Patrick? Okay, if it's a crappy thing, then tell me, and then we'll come up with something else later. Yeah. All right, great. So didn't go too much over time, and tomorrow we will have a lot of fun with naphthyridines and case studies. So if you have a chance to look at the book for 5 minutes today, please do so. That was ancient times, so I think they might have done that. It's not. All I know is that years immediately preceding chloroquine, the spider seals. They use butter or molasses. Yeah.
That's really interesting because the chloroquine was what, 1950 or something like that?
46.
So, like, as far as I know, by 1910, the Danish had like farms and farms and millions of pounds of synthetic alkaloids coming out each year.
Yes.
So I don't really understand why then that wouldn't be getting transported everywhere, because with World War II and I going on, the theaters of war were everywhere, right?
It's true, and I think that the drive to do chloroquine was just trying to find something simpler that they didn't have to rely upon that source.
And the importing, I think, was a problem too, because you had to get through
No
enemy
FedEx.
territory to bring it over, right? You had to hit the jungle. So
Yeah.
I was just curious.
Yeah, no, I don't know the exact day, but yeah, that was pretty commonplace.
That's
Yeah.
wild.
Yeah.
Thanks, Bill.
Yeah. Sure.
Hey guys, would you mind helping me with the chalkboard once you get done? Really early when I started teaching did I realize how difficult it is to make
Good chalkboard
a chalkboard look like this at the end of a lecture. I've worked hard. I'm definitely a lot better than when you guys took the class. And I think the key is to come in early so you're not as under the time pressure to draw. It's really amazing. There's some art. Art.